Welcome to physics, and today I'm going to talk about, and I'm going to derive the electric field due to a dipole along the axis. Okay, so what is a dipole? A dipole is two charges. It's an object that has two charges where the charges have the same but opposite value and they're separated by some distance. And you may think, oh, well, that's just a silly problem. It turns out that this shows up a lot of places, that things are either actual dipoles or they act like dipoles, so it's a really important problem. So we want to find the electric field. Let's say this is the origin. Let's just make it like that. And this is the x-axis. I want to find the electric field along this axis. And then on another video later, I'll do along this axis. And then another video I'll do anywhere in the universe. The whole universe. I'm going to do anywhere in the whole universe. Okay, so now a quick review. If I have a charge, Q, and I want to look at a point somewhere, a distance, a vector location R from that point charge, there will be an electric field. The value of that electric field, it's a vector, is going to be equal to 1 over 4 pi epsilon naught, where 1 over 4 pi epsilon naught is equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. It's a constant. Q is the value of the charge. R is a unit vector pointing in the same direction as R. And R squared is the magnitude of that squared. So that's the value, the electric field due to one charge. What if I have two charges? Well, if I want to find the electric field right here due to these two charges, I just have to find the electric field twice and add it together. And that's what I'm going to do. Okay, let me move this mic a little bit. I'm setting up a new system here, and things may not be perfect, but I will make it better as time goes on. I promise you. So let's just pick, this is the vector. I want to find this is the vector R. So I have two electric fields. I have the electric field due to the positive charge, and since this is positive, it's going to be pointing away, and I should draw it in red. So I have this, and I'll call that E plus, because it's due to the positive charge. And then I should have done blue, but I have green. And then I have this, E negative. And you'll notice if you think about this, the positive charge is going to be closer to the point of observation. So this R for this charge is going to be smaller and therefore make a greater electric field than this charge, even though it's a little bit further away. Okay, so let's just get down to it. I want to write down this E plus. E plus is going to be equal to 1 over 4 pi epsilon naught Q, and I'm just going to call this positive Q and that negative Q. So it's Q over this vector. Okay, so this vector is going to be R plus. And where R plus, I should write it right here. I'll just write R plus. R plus squared, and then R plus unit vector. So what is R plus? Well, R plus is going to be equal to this vector from here to there minus this vector. So this vector right here is going to be equal to, so this is going to be R. Is that right? R final minus, yeah. R minus the vector. So what's this location of this? It's going to be at S over 2, 0, 0. And I'm using this bracket notation for vectors. That's just the way I like it, because that's the way my favorite textbook does it. So this is the vector. Since this is the distance S, this is the distance S over 2. So now I can write R plus, R, and I'm going to call this as the vector X, 0, 0, because it's in the X direction. So now I can write E plus. E plus is going to be equal to 1 over 4 pi epsilon naught Q. R plus is going to be equal to this. I can write this out. It's going to be equal to X minus S over 2, 0, 0. So the unit vector for this only has a component in the X direction. So the unit vector for R plus hat is just going to be 1, 0, 0. So let's write that as 1, 0, 0. Now, for the magnitude, it's going to be equal to the magnitude of r plus squared. I'll write it up here. R plus squared magnitude is going to be equal to the square root of this squared, x minus s over 2 squared, plus 0 plus 0. And then if I square that to put into this formula right here, then I get just this piece right here. So I get x minus s over 2 squared. And that is the electric field due to the x component. To the positive charge. Now we need to do the same thing for the minus charge. Well, let's go ahead and write r minus is going to be equal to r minus negative s over 2, 0, 0. So that's going to be equal to x plus s over 2, 0, 0. Right? Because this one's going to be further away. And then r minus magnitude is going to be equal to the square root of x plus s over 2 quantity squared, plus 0 plus 0. Okay, let me put a box around this because I don't want to lose it. If you put boxes around things, you don't lose them. Oh, and a good thing I checked. Look, I almost lost that. Okay, so now I get e minus, it's going to be the same thing. It's going to be 1 over 4 pi epsilon naught. Now I have a negative charge, so I have negative q over this squared, so it's going to be x plus s over 2 squared times the vector 1, 0, 0. And I'll put a box around that. And it's green. So now I just need to add these two together. So let's do that on a separate sheet of paper. So I have E equals E plus E minus. And that's going to be equal to 1 over 4 pi epsilon naught Q over x minus s over 2 squared, 1, 0, 0. And then the other one is a minus, so it's going to be minus 1 over 4 pi epsilon naught Q. See, I had the minus Q, let's put the minus right there, over x plus s over 2 squared, 1, 0, 0. We can simplify this. I can factor out the 1 over 4 pi epsilon naught Q, and then I have 1 over x minus s over 2 quantity squared minus 1 over x plus s over 2 squared, and then they have the same unit vector, 1, 0, 0. So now what I want to do is I only care about the x component. So let's just consider EX. EX is going to be equal to 1 over 4 pi epsilon naught Q. Now I have this stuff. Okay, I want to get a common denominator here. So this is x minus s over 2 squared, and this is x plus s over 2 squared. So if I multiply this by x plus s over 2 squared on the top and the bottom, I get x plus s over 2 squared. And then I get x minus s over 2 squared times x plus s over 2 squared. And now for the same one over here, I multiply by x minus s over 2 squared over x minus s over 2 squared, and I get minus x minus s over 2 squared over that. Are we having fun now? Okay. Now, let's multiply this stuff out up here on the top. So I get equals 1 over 4 pi epsilon naught Q. Now this is, I'm going to get x squared, and then I'm going to get 2 of these terms. So I'm going to get plus 2x s over 2, which is just xs. And then I'm going to get a plus s squared over 4. Now on this side, I'm going to put the minus right there. I'm not going to factor that out. I get x squared, and then again I'm going to get a x times s over 2 times the negative s over 2 plus s over 2 times x. So I get minus xs. That's right. Okay. And then I get plus s squared over 4. And all of that is over x minus s over 2 squared plus x, times x plus s over 2 squared. Okay, look what's happening here. Here I have an x squared, and here I have a minus x squared, right? So those cancel. Let's cancel in red. Red cancels, right? Cancel. Cancel. This I have xs, and then I have minus xs, minus a negative xs. So those don't cancel. They add up. And then here I have an s squared over 4 minus s squared over 4. Cancel, Rama. Okay, so now I get this. 1 over 4 pi epsilon naught q times, I have an xs plus xs. So I get 2xs. I think of that band in excess, right? Okay. And then over this, x minus s over 2 squared, x plus s over 2 squared. That's the answer. That's my x component of electric field. And, I realized I'm looking at this and my handwriting's really messy because I think what I had my other board was a little bit higher and I think I could write a little bit better, but I'm going to have to fix that. Okay. I'm just talking out loud here. So what if x is much greater than s? If x, well, let me check something first. Let's check. So remember that the magnitude of the electric field due to a point charge is E magnitude is 1 over 4 pi epsilon naught q over r squared. That's the magnitude. And so this has to have the same form, right? It has to have the same units. So it has a 1 over 4 pi epsilon naught. That's good. It's got charge over distance squared. Does this have charge over distance squared? Well, this is distance times distance on the top. It's got the charge. It's got meters squared. And then here on the bottom I have meters minus meters, so that's going to be meters squared, and then meters plus meters squared. So this is meters squared times meters squared, which is meters to the fourth. So I have meters squared divided by meters to the fourth. So I do get 1 over meter squared. So that's good. The units check out. Okay, now what if x is much greater than s? If that's the case, then this term right here is going to be approximately x. And this term is approximately x. So in that case, E magnitude, let's call this E magnitude, is approximately equal to 1 over 4 pi epsilon naught 2 qx, I should call that r, but that's fine, over x squared times x squared is x to the fourth. And so this is going to be 1 over 4 pi epsilon naught 2q. Oh, where'd my s go? Oh, s. 2s. S over x cubed. And that's it. That's the far field approximation for the electric field due to a dipole. And that's where x is the direction of the field. Okay. Now you may think, wow, that was a lot. We're done now. No, we're not done. Because I want to plot these two, right? Because there's no approximations here. There is an approximation there. So let's just see how well these two approximations add up to each other. So I'm going to switch over. I'm going to do this in Python. And let's do this for the following case. I think I already picked a value here. Let's say I have this minus plus, and this is 1 nanocoulomb, negative 1 nanocoulomb, and S is equal to 0.001 meter. I don't even know if that's realistic or not. But what I'm going to do is just start over here. So this is we'll put that at the origin. We'll start right here at, let's say, I don't want to start right here because it'll get too big. Let's start at x equals 0.003. And then I'm going to calculate the electric field. I'm actually going to do it, I'm not even going to use this formula. I'm going to do it exactly, right? Because I can calculate the electric field E plus plus E minus, it's pretty easy. And then I'm going to plot that, the X component. I'm also going to plot this, and we'll see how close they get. Okay, so let's switch over to Python. Move the microphone. Hopefully you can still hear me. And click my thing. Okay, so I think you can see that. So I've already put in my charges. Let's go ahead and make a graph. tgraph equals, and I will give you the code. X title is going to be equal to X in meters. And then the Y title is going to be equal to EX. And the units are going to be newtons per coulomb, or volts per meter, whatever you prefer. And then I'm going to say FE is going to be the G curve. Color equals color.blue. And let's give it a label. Exact E. X. And then let's put this at FD for dipole. Let's call it FA for approximation. That's going to be G curve. Color equals color.red, because approximations are red. I don't know if you knew that. And then label equals, let's call it far field, because it makes me think of Mission at Farpoint from Star Trek. Remember that? That was Next Generation. Okay, so now I need to start with my value of my X, which is X equals 0.03. You know, I think I am just going to use this formula. Let me move my formula over here, because if I don't, I'd have to put a location of the charges and stuff. I'm just going to use my exact formula and my other formula. So let's just say I need a D. 0.003, I said. Okay, dx, how big of a step size do I want? 0.0001. That'd be 10 steps per millimeter. That's fine. And let's say while x is less than 0.00, let's say 0.1. Let's just see how that goes. Okay, so the first thing I'm going to do is calculate E exact. I'm going to call that EX for exact and for X component. And it's going to be equal, oh, and I do have, so up here I put K instead of 1 over 4 pi epsilon naught. Okay, that's fine. K times Q times 2 times X times S divided by parentheses X minus S over 2 squared. And here I get scared. I'm going to put an extra parentheses right here. Over parenthesize times parentheses X plus S over 2 squared. That's that one, okay. And that's it. And then I'm going to calculate the approximation. EA is going to be equal to K times 2 times Q times S divided by X cubed. Now I'm going to plot them. So FE dot plot, the X value is going to, the X component is, the X position coordinate is going to be X, the Y coordinate is going to be EX. FE FA dot plot XEA, and then I need to increase X. X equals X plus DX, right? Because I need to move over a little bit. And I think that might be it. Let's just see. Dipole test 1. Save it. What do you think? Do you think this is going to run the first time? I don't know. It seems like it never does, but that's okay. I'm kind of scared. When it does this, I just get scared. And then I think maybe it never ends. Oh, it did something. Aha! I misspelled title. X tilde. Title. Is that all it was? Title. Okay, let's try it again. No. GS power is not a function. What the heck? Is not a function. So EX. K times Q times 2 times X times S divided by, I think I'm out of parentheses or something. Divided by, okay, that one goes with that one. That one goes with that one. That one. Oh, times, aha. Whew. See, it's the silly little things, right? There, well, that's really nice. Look at that. They're pretty close. Okay, so you see here that there is a difference. And so what I want to do is actually get a little bit closer in. So this is 0.7, 0.6. Let's go from up to 0.06. I don't need to go further than that. And let's start at 0.2 and just see what happens. So shift it down. And I don't see my label. My label should be in there, but you can see the difference. So the blue is the exact, and the approximation is the red, and they do different. But once I get over to, I'm still pretty close, and the difference is just tiny. Now I do want to do a couple more calculations with dipoles, but I think this is a good place to stop. And I'll share this code with you down below, and I think that's enough for that. I do want to see this graph. Let's see. How do I see the graph? Not sure why I didn't show the graph. Oh, there it is. See, there's the label. I just made it too big. Let's just fix that because it's really kind of bothering me. So when I go up here to graph, I can go up here and say, oops. I can add in width equals 400. Let's see if that does it. Oh, that's too small. Well, that's fine. So then now it fits in there. That's kind of cool. Okay, there you go. I'm going to make another video on dipoles. Hope you like this. Oh, and if there's things that don't work or that don't make sense, comment down below, and I'm going to answer those comments. I don't know if you know that, but I actually do read the comments. So I'll talk to you guys later.